All right, so we are starting in chapter 6 today. And when it comes to chapter 6, there are a couple of main big idea concepts that are at the very heart and core of this chapter. Now, this was one of the things that was covered in your pre-reading, pre-assignment to today, the idea of Avogadro's number. What we need to understand about Avogadro's number is that Avogadro's number is just a counting unit. So the videos that I had you do kept talking about the concept of a dozen. If I have a dozen jelly beans, I know that it's 12. If I have a dozen eggs, I know that it's 12. If I have a dozen popsicle sticks, I know that there are 12 in that group. Avogadro's number is kind of the same thing, only we don't call it Avogadro's number when we're describing it, we call it a mole. 1 mole of a substance is Avogadro's number, 6.022 times 10 to the 23rd of whatever that thing is. So a mole of jelly beans has 6.022 times 10 to the 23rd, 602 sextillion objects in it. Well, in that case, jelly beans. A mole of popsicle sticks has 602 sextillion popsicle sticks in it. So, conceptually speaking, a mole is just a stand-in for a number, and that number happens to be Avogadro's number. Now, we're rarely going to think about things in terms of Avogadro's number because it's just so stinking big. To put it into another context, because goodness, we couldn't have enough analogies for this. The physical distance of the universe. So if I was going to take a ruler from one end of the universe to the other end, is estimated between 600 and 700 sextillion miles from one end to the other. And it's constantly expanding. Well, 602 sextillion is a mole. And so let's just say that that estimate happens to be right around there. There is 1 mole of miles from one end of the universe to the other. That number has no frame that we can possibly put onto it that makes any kind of sense to us up here. So we very rarely use it in this kind of context. What we tend to use the concept of a mole to try to describe instead is we try to relate it to things that we can measure. And probably the easiest thing that we can measure that would be a reasonable quantity for us to kind of put our arms around is the concept of mass. I can walk up to a balance, put this bottle on it, and the balance would tell me how much this bottle weighs. We have defined mass according to the carbon-12 isotope. By definition, 12 grams is equal to 1 mole of carbon-12 atoms. That's how we've defined mass for ourselves. Seems a little bit weird, seems a little bit kooky, but every definition system has to have its start. And even the units that we take for granted work in the same kind of way. What is a second? Well, a second is 1/60th of a minute. What's a minute? A minute's 1/60th of an hour. How did I even come up with those? How do I know what a 1 second is? Well, there's some isotope that oscillates and the measurement of the oscillations of that isotope give us the definition of 1 second. That's the definition. How big is a meter? Back when the meter was invented, it was literally a bar of a certain length. And that's what we based the measurement of a meter on. So this definition allows us to put a link between the concept of grams, which we can easily measure, and atoms, which we cannot measure easily at all. And the mole helps us to make that bridge between them. Because the moles are the bridge, they make great conversion factors. Knowing that there's Avogadro's number of particles in a mole of any substance, I can use Avogadro's number to convert between moles and particles. I can do so relatively easily. If I have a number of particles, so let's say that I'm trying to figure out how many moles of carbon are in a particular group of atoms, I can take the number of particles that I know that I have, divide it by Avogadro's number, and it would tell me the number of moles that were there. If I knew that I had 0.5 moles of something, I try to figure out how many particles it was, I can take that 0.5, multiply it by Avogadro's number, and get a pretty decent estimate of how many particles, how many atoms were there. The tie together for this is something that we have seen before. This is unit conversion. This is the very essence of some of the calculations that we've been doing kind of all this time. Anytime we want to convert one thing to another, we use dimensional analysis to do so. So we've used this to turn miles into kilometers. We've used this to turn minutes into seconds. We've used this to turn joules into calories. We can use it here to turn things into moles and turn moles into other things. But again, the concept that is kind of itching at us is the fact that it's not conceivable to measure individual atoms. If I'm doing any kind of chemical reaction in the lab, I'm not going to measure out individual grains of calcium chloride or even individual atoms of carbon. It doesn't make any sense to do so. I'm going to fall on my strengths. My strengths are measurement, balances, mass. And so the overall concept of something called a molar mass begins to come into focus for us. Because what a molar mass does is it tells us how much does 1 mole of this particular substance weigh. And where we get the values for that come directly from the periodic table. And so this is one of the beauties of the design of the periodic table, and one of the reasons why we defined the mass to particle relationship the way that we did with carbon-12 and all of that other stuff. What the periodic table tells us is 2 things. If I am interested in the mass of an individual atom of a particular element, all I have to do is look to the table, and that particular unit is something called atomic mass units. So if I look at the periodic table, helium is 4.003 on the periodic table for its mass. What that tells me is that one atom of helium weighs 4.003 AMUs, atomic mass units. Now, again, atomic mass units don't make a whole lot of sense to us because it is the rarest of occasions where we are going to use individual atoms of anything. Of more use to us is the molar mass. That molar mass also comes off the periodic table. It tells us that that same helium, 4.003, if the unit is grams, that's how much a mole of that atom weighs. So 1 mole of helium weighs 4.003 grams. 1 mole of carbon weighs 12.01 grams. 1 mole of chromium weighs 51.996 grams. All I need to do, look at my periodic table, whatever that value is in there for mass, that is the mass of 1 mole of that element. This same logic can be applied to compounds as well. So if I'm trying to find the mass of a compound, whether that is a molecular compound or an ionic compound, the process is the same. That chemical formula tells me how many of each element there are, and all I need to do is add together those masses. So, for example, carbon dioxide. The molar mass of carbon is 12.01. Molar mass of oxygen is 16.00. To find carbon dioxide, I need to take the mass of 1 carbon and the mass of 2 oxygens, because there are 2 oxygens in the compound. So carbon 12.01 plus 2 times 16 for oxygen. Add those together, 44.01 is the mass of carbon dioxide. Now, again, if I'm looking at things from a molecular standpoint, the unit there is AMUs. If I'm looking at this from a molar standpoint, which is what we're doing most of the time, the unit here is grams per mole. And so I can do this literally with any compound, any substance that I can think of or dream of. All I have to do is look at the chemical formula and add together the molar masses of those elements in that compound. Just making sure that if I have more than one atom of that element, I multiply by that number. So I multiply by 2 here because there are 2 oxygens in the form. So I'm going to present this concept to you. This is what I call a concept map. And in this particular concept map, and I will give you a copy of this electronically as well as in print. I'll give you the print one on Wednesday. I'll pull this out and give it to you electronically after class. This is a real, I don't want to say lifesaver, but this is a really great organization. Because what it tells you is if I'm trying to do some kind of a calculation, I can use this to figure out what kinds of information I need to do the proper conversions. So if I'm trying to figure out the mass of a number of molecules of a compound, then what I can do is I realize, okay, I need to go from molecules to moles first, and then from moles to mass. There's going to be 2 different conversions involved here. The first one is going to involve Na. Na is Avogadro's number. The second is going to involve capital M. Capital M is molar mass. Now, we'll get to, as we go through this chapter, there are two sides to this. There's a side that involves atoms and elements, and a side that involves molecules and compounds. And there's actually a way to go between the two formula, but that's not something that we're going to talk about today. But it is definitely possible to go between both zones, both worlds here. Let's take a look at some practice problems. How many moles of potassium atoms are present in 19.5 grams of potassium? So if I go back to my organization chart here, I want to know, I've got the mass. I want to convert it into moles. Now the chart here says specifically to go in this direction, I'm going to divide by the molar mass. And that's certainly true. But let's take it from a dimensional analysis standpoint, because we know that if we go with the dimensional analysis route, we do the same process for any conversion and not have to rely on, okay, well, in this case I divide, and in this case I multiply. It's a lot easier to just track the units with the dimensional analysis. So we start with our 19.5 grams of potassium. Using our dimensional analysis, we know that we want to go from grams of potassium to moles of potassium. And the gateway between the two is molar mass. Molar mass for potassium, I can pull off my periodic table. It is 39.10 grams in every mole. My grams of potassium cancel. And so, yes, I am dividing by the molar mass, but I can see organizationally why I need to divide by the molar mass using the dimensional analysis here. 19.5 divided by 39.10 to 3 significant figures, because I started with 3 here. I've got 0.499 moles of potassium. Second question here, how many formula units are present in 5.32 moles of baking soda? So just to refresh your memory here, a formula unit is just a way of saying ionic molecule, since ionic compounds really don't have individual molecules because they're those 3D crystal arrays. So this is a moles to particles calculation. So NaHCO3, sodium bicarbonate. Again, I can go back to my organization chart here. And it's going to tell me that to go between moles of a compound and molecules or formula units, I'm going to need Avogadro's number. So the conversion here, 1 mole of sodium bicarbonate is Avogadro's number, 6.022 times 10 to the 23rd formula units. So 5.32 times Avogadro's number to three significant figures again. My moles are going to cancel out. We get 3.20 times 10 to the 24th formula units of sodium bicarbonate baking soda. So the real trick in here is just recognizing what number you need to use in what situation. And the key word that you always want to look for in these kinds of problems is some kind of a particle term. Either particles itself or atoms, molecules, formula units, ions, those kinds of things. Those are going to tell you that that you need to use Avogadro's number in this conversion. And certainly, if you are starting with a scientific notation kind of number, that's also usually a clue that you're going to use Avogadro's number as well, because very rarely are we working numbers that big otherwise. Questions about either of these two practice problems? All right, let's take a look at another one, and I'm going to let you try some on your own. How many moles are present in 58.4 grams of chalk? Chalk is calcium carbonate. So to do this problem, I need to do two things. Since I'm going between grams and moles, I need the molar mass of calcium carbonate. And I need that before I can do any kind of converting. So for calcium carbonate, again, we got to break it down into the components. I have calcium and carbon and 3 oxygens. The calcium is 40.08. The carbon is 12.01. And there are 3 oxygens, and each of them are 16. And so the molar mass of calcium carbonate is the sum of all of these. So 40.08 plus 12.01 plus 3 times 16, we get 100.09 grams per mole. Now, as you get familiar with doing this, you're not going to need to break this out. You're going to just be able to look at it and go, okay, I need a calcium, I need a carbon, I need 3 oxygens, and you'll just be able to pound those out on your calculator. This is just an organization, helping you to kind of see where all the numbers are coming from. Like I said, if you get good at it, when you have enough practice with it, you're just going to know automatically that that's what you're supposed to do. So the need to write out each one of these calculation steps won't be necessary. But we do need to know the molar mass, and there it is. Now it becomes a question of turning it into moles. So I start with my 58.4 grams of calcium carbonate. And this is my conversion factor now. 100.09 grams in 1 mole. My grams of calcium carbonate cancel. 58.4 divided by 100.09, the 3 significant figures, 0.583 moles calcium carbonate. All right, questions with this example? All right, as promised, I'm gonna give you an opportunity to try to work some of this out on your own. Start with this one. How many moles of helium are in a 3.5 gram sample of that gas? For this type of question, is this an Avogadro's number question or is this a molar mass question? This is the kind of recognition thing that can really help you to go in the right direction right from the start. So if it's an Avogadro's number question, you're looking for one of two things. Am I dealing with a large exponential number here? No, 3.5 is not large or exponential. So that one, take that one off. Am I asked anything about particles, atoms, molecules, formula units, anything like that? No. So if the answer to both of those questions is no, then you should know that you are in a molar mass kind of question. We need to use molar mass to be able to solve the problem. If you are dealing with a large exponential, or you are asked something about particles, atoms, molecules, and the like, those are triggers. That should trigger you to Avogadro's number and using that number as a conversion. So since we have neither, we know that we're dealing with molar mass. And so from that standpoint, we need to take this 3.5 grams of helium and we're going to convert the helium into moles using the molar mass. Molar mass of helium, 4.00. So 3.5 divided by 4.00. My calculator says 0.875. And so I know a lot of you had that number in. I could see it as you were responding. But what we have to keep in mind is from a significant figure standpoint, I've got 2 digits in this number and 3 in this number. When I'm multiplying and dividing, the fewest is what I round to. So I need to round to that second digit. 0.88 moles would be the correct answer. If you put in 0.875, you got most of the credit. I would have dinged you for the sig figs there. You'd have got one of those wonderful sig figs minus a quarter written on your quiz form as a result of it. All right, questions here. All right, let's try another one. How many carbon atoms are in a sample containing 9.913 moles of carbon? Just as a hint here, instead of writing out scientific notation, use the capital E to take its place. So I was putting an Avogadro's number instead of times 10 to the D there, I was writing for the times 10 part. That way you don't have to worry about trying to fix subscripts and superscripts and that kind of stuff. Now, right off the deck, ask yourself those 2 questions. Am I dealing with a large exponential? No. Am I being asked about particles? Yes. Being asked about atoms. So Avogadro's number is going to be key to this particular conversion. All right, the conversion here. So if we're using Avogadro's number, 1 mole is Avogadro's number of carbon atoms. So my moles are going to cancel out. Carbon atoms would be what is left over. 0.913 times 6.022 times 10 to the 23rd is going to give me 5.50 times 10 to the 23rd carbon atoms. So a couple of places that you could have gone wrong here. Obviously, around properly. If you divided instead of multiply, you would have ended up with something times 10 to the negative 22nd, I believe. Which obviously would have caused you a little bit of problems there. You're on the wrong scale. The reason you're on the wrong scale is because you pay close enough attention to what the numbers were and how they canceled out. Other issues, if you're still having calculator issues in terms of not knowing how to input scientific notation properly into your calculator, come see me after class. I'll try to straighten you out a little bit, because that's a real common issue that you can run into pretty easily. All right, so one last concept that I want to cover today, kind of looking ahead. What if I had multiple calculations? So all the calculations we've done thus far have been one-step calculations, where I'm turning grams into moles or I'm turning moles into particles. What if I have to go between grams and particles, or particles and grams? What would I need to do? What would I want to do in that kind of a situation? Well, the organization for that can still be found here on this map, because what we're ultimately doing is we're going to need two conversions in that process. One conversion gets moles, and one conversion gets from the moles to the mass, or vice versa. So the real key to this kind of question is just understanding that moles here is going to be a bridge for us. We're going to use moles to connect the thing that we are trying to determine to the thing that we know already. So if I have a question like this, where I'm starting with 16.21 grams of aluminum, I can do a two-step conversion where I know I'm going to need to convert to moles in the middle. But my first step would be, let's turn that grams of aluminum into moles of aluminum. To do that, I need the molar mass. The molar mass of aluminum is 26.98 grams. So that step cancels out my grams. Now in my other step, I need to turn the moles of aluminum into aluminum atoms. And here, since we're talking about atoms, now we know that we need to use Avogadro's number, 6.022 times 10 to the 23rd in 1 mole. So in total, I have 2 sets of calculations to do. Now, because I'm doing dimensional analysis, I can do all of those calculations at once. I just need to multiply across the top and divide across the bottom. So 16.21 multiplied by Avogadro's number, divided by 26.98. And in this case, I'm going to have 4 significant figures, because I have 4 here, 4 here, and 4 here. It would be 3.618 times 10 to the 23rd aluminum atoms. So if you see more complicated conversions like this one, that's really all that you need to do with it. Is just take that step and extend it to one more step. So we're basically just putting two steps together here instead of just the one. As we close out for today, and you get ready to take on this post-lecture assignment that's due tomorrow night, give me a little bit of how do you feel about this particular set of calculations. Hopefully after the assignment, you'll feel even better still about those, but if you don't, make sure that you leave me some feedback or some comments at the end of that post-lecture assignment, and we'll start from there on Wednesday. Have a good afternoon.